Good afternoon, all of you. In the previous class, we studied about entropy and how entropy is related to spontaneity. And today we are moving on to our next term, which is Gibbs energy and how Gibbs energy is related to spontaneity. And when we told about spontaneity, we told that there are two factors which affect the spontaneity, or there are two deciding factors or driving forces for spontaneity, which was the entropy or the disorder, and one more factor was the enthalpy or energy. So entropy and enthalpy was two factors which were leading the spontaneous reactions, and those two factors are combined in a term which is Gibbs energy. And Gibbs energy is a particular energy which is actually used in a reaction. So Gibbs energy is a term which is a combined form of entropy and enthalpy, plus Gibbs energy can also be told as the energy which is actually used in a reaction. For example, in a reaction, we are trying to boil water. So we are trying to boil water in a vessel, and are we using the whole amount of energy for just boiling the water? No, some amount of heat which we provide may be used for heating the vessel. So that energy is not actually used for boiling water. It is gone as waste. So that energy is wasted in the reaction. The one or the energy which is absorbed by the container and energy which goes out for the surrounding, all those energy is actually wasted in the reaction. So the exact energy which is actually used for the heating or boiling of water is the only energy which is used in the reaction. So the energy which is actually used in the reaction, and that energy is known as Gibbs energy. And now we will see how the Gibbs energy is related to spontaneity. So the mathematical expression for Gibbs energy, which is G is equal to H minus Ts. So the Gibbs function G is equal to enthalpy H minus temperature T into S, which is entropy. And here we have a relation between H, the enthalpy, and entropy. So enthalpy and entropy combiningly we got in an equation. And if we try to find out what is the change in Gibbs energy, how the equation will be, or we are going to find the equation for delta G. So that delta we have to add in all the cases. That's all what we are going to do. So delta G is equal to H system minus T delta S system minus S delta T. And G is an extensive property and a state function. So it depends on the quantity of the system and it is independent of the path. So coming back to this equation where we were finding the delta G or change in free energy of a system. So we were substituting in this equation. So we got delta G or change in free energy is equal to change in enthalpy minus, now this term we are splitting into two. In first case we are keeping the T like that and we are considering change in entropy, just the change in entropy, and in the next term entropy is kept like that and we are changing the temperature. So delta G system or change in free energy is equal to change in enthalpy minus temperature into change in entropy minus entropy into change in temperature. So that's how we got this equation, and now we are keeping the temperature constant. So at constant temperature, when the initial temperature and final temperature is the same, so change in temperature will be equal to 0. As initial and final will be same, so T1 minus T2 is equal to 0. So delta T is equal to 0. So when delta T is equal to 0, in this equation, this term is 0. So hence the whole term will become 0. So delta S into delta T will become 0. The whole term is eliminated. So the remaining will be delta G system or change in free energy of the system is equal to change in enthalpy minus T delta S. So that becomes the equation. And when we avoid the system which is the subscript here, we will get the equation for delta G or change in free energy, which is equal to delta G is equal to delta H minus T delta S. So this is a very important equation of thermodynamics which gives us the expression for free energy. And now what we need to find is, we have to find the unit of free energy. So from this equation we can find it out. So actually the delta G has a unit of energy. But how we got the unit of energy for delta G? Because both delta H and T delta S are energy terms. So delta G is equal to delta H minus T delta S, and all these expressions are actually energy terms. So delta H is change in enthalpy. So enthalpy is a form of energy. And what about T delta S? So T delta S, temperature is in Kelvin form. So temperature, the unit is Kelvin, into the entropy is H by T or enthalpy by temperature. And that unit will be, for enthalpy it is joules as it is energy, and divided by T. T is temperature and therefore we wrote Kelvin. So Kelvin of this one, and for enthalpy we have J by K. So hence totally it becomes K into J by K. And one of the K is in the numerator, another is in the denominator. We can cancel off both of them. So hence finally we got J. So for T delta S we have the unit J. So for T delta S we have J, and for delta H also we have J only, as it is an energy term. So this also is in joule and this also is in joule. So hence totally delta G also we can tell in joules. So again if I tell, so delta G is of having a unit of energy. So delta H and T delta S are the terms which is involved in delta G. So energy change, the unit will be joules, and we are just concerned about the T delta S, and out of T delta S, T will have a unit of Kelvin. So Kelvin is a unit of T, and we need to consider delta T. So Kelvin into unit of entropy is written here. So entropy is enthalpy by temperature. So enthalpy we have given as joule and temperature we have given as Kelvin. So K into J by K. K is of T and J by K is of delta S. So hence K into J by K, we can cancel off the K in the numerator and denominator. Hence we get the unit for T delta S is equal to J. So delta H, as we told, it is actually J, and T delta S is also J. So as both of them are joules, hence finally delta G also will be represented in joules. So with this we found out the equation and unit for delta G or free energy. And now we need to find out how delta G is related to spontaneity. So for that we will consider some equations which we did yesterday. So this is an equation which we studied yesterday, which is delta S total. The total entropy change is equal to entropy change of the system plus entropy change of the surrounding. This we have learnt yesterday. And yesterday we studied that delta S is equal to Q by T. Hence we can tell that entropy change is equal to enthalpy change by temperature. So if we consider the surrounding or entropy change of the surrounding, it will be equal to the enthalpy change of surrounding by temperature. So how much is the change in enthalpy of the surrounding by temperature is equal to the entropy change of the surrounding. So how much is the enthalpy change by temperature is equal to entropy change of the surrounding. And one more thing we need to know is at constant temperature. So when the temperature is not changing, if we consider a system and if the system gives out some amount of enthalpy, so the system is giving out some amount of enthalpy, then it will be the same amount of enthalpy absorbed by the surrounding, right? So whatever is absorbed by the surrounding is actually given out by the system. So the same amount of enthalpy will be given out and same amount of enthalpy will be absorbed by the surrounding. So hence we can tell how much ever is the enthalpy of the surrounding, the same amount of enthalpy will be given out by the system. So that enthalpy will be equal to negative of delta H system. So the enthalpy change of the surrounding will be equal to the enthalpy change of the system in opposite sign. So we are telling how much ever is the enthalpy change of the system and that was given out which was absorbed by the surrounding. So it will not be any change for the enthalpy of system and enthalpy of surrounding when the temperature is constant. How much ever is given out, that much only will be absorbed by the surrounding. So we can tell delta S surrounding or the entropy of the surrounding is equal to negative of delta H system by T. And this equation we are going to substitute in this equation. So delta S total is equal to delta S system, we will write like that only, but the delta S surrounding we will substitute with this. So the total entropy change is equal to change in entropy of the system plus minus of the change in enthalpy of the system by T. And now if we rearrange the above equation, what we get is we multiply T with all the terms. So we multiply T with this term and this term and with this term. So when we multiply T with this term, this T and the multiplied T will cancel off. Hence the remaining delta H system only will be there. So all this when we write here, T delta S total is equal to T into delta S system minus of delta H system. As the T and T got cancelled, minus of delta H system. Actually we are trying to get the equation for free energy from this equation. So that's why we are rearranging this. So T delta S is equal to T delta S system minus delta H system. And now we are going to apply the condition for spontaneity. For a spontaneous reaction, delta S total is greater than 0. So delta S total or this term is greater than 0. Hence we can tell the T delta S minus delta H system is also greater than 0. So once this term is greater than 0, we can tell that T delta S system minus the answer for this term, which is T delta S system minus delta H system, is also greater than 0. So hence we can write, we are taking this negative outside. So hence we get negative of delta H system minus T delta S is greater than 0. So ultimately what we need is the equation of free energy from this equation. That's why we do all these changes. So this term came to this side and we took the negative outside. So hence we got negative of delta H system minus T delta S system greater than 0. So if you don't understand this conversion, just ask me in the group. So minus of this much term is greater than 0. So this term you remember, so which is minus of H delta system, minus of delta H system minus T delta S system greater than 0. So how can we relate this equation with the equation of delta G? So this term and this term is same, but the only change is a negative charge. So this term and this term is same. So we can tell negative of this term is greater than 0. So hence we can tell negative of delta G also will be greater than 0. So as negative of this much is greater than 0, we can tell negative of delta G is also greater than 0. So for a spontaneous reaction, negative delta G is greater than 0. So delta G is less than 0. As negative of delta G is greater than 0, delta G will be less than 0 for a spontaneous reaction. So at constant temperature and pressure, if delta G is negative, then the process is spontaneous. That's what we found out from this much of equations. So finally we got, for a spontaneous process, delta G is less than 0. So hence, if delta G is negative, then we can tell the process is spontaneous. So if free energy is negative, then the process is spontaneous, and if free energy is positive, then the process is non-spontaneous. This is just opposite of entropy, which we discussed yesterday. Entropy, we told, if entropy is positive, the process is spontaneous, and if entropy is negative, we told the process is non-spontaneous. So just opposite of entropy, we have the free energy. So you can compare this and study. So in this term, delta H system is the enthalpy change of the reaction, and if this is the enthalpy change of the reaction, then delta G is the energy which is actually used. So what will be T delta S? So T delta S is the energy which is not used. So delta G is the energy used. So delta H is the enthalpy change of the reaction. So hence we can tell this is the unused energy. So T delta S system is the energy which is not available for useful work. So this is the energy which is not used, and delta H is the total energy and delta G is the energy which is used. So delta G is the net energy available for useful energy, and which is also known as free energy, and delta G is also known as Gibbs free energy. So useful work is equal to total work minus unused work. That is a common equation. And when is the condition where we can get the delta G as a negative value? For that, we need to get either T as a great value and delta as a small value, or just the opposite. The delta S should have a greater value and T should have a smaller value. Anyway, this should cover up this value, then only we will get delta G as a negative value, and that time only the process will become spontaneous. So with this we wind up our session. So please read the textbook and prepare notes. Thank you.